Okay, so our next mod here is synchronous motors. So we just finished alternators and the generation of an AC voltage. So now we're going to see a load that we will hook up. So an AC motor, again, a very specific type of motor, a synchronous motor. Um, we haven't really talked about AC motors in fourth yet. We did talk about squirrel cage induction motors in third. And they're going to be somewhat similar to an alternator, these synchronous motors, but also similar to a squirrel cage induction motor for their starting. So we'll cover that coming up here, but again, we'll go through this information from your ILM and hopefully clear some stuff up. Again, I do have other videos posted in the course, and I will obviously do any questions on the fly that you guys need as well. But there's a few calculations, more just an understanding of a phasor diagram more than anything. So first off, we'll talk about their applications, and then we'll talk about their advantages and disadvantages and how they're constructed. So again, synchronous motors operate at synchronous speed. Synchronous speed, for what we used in third, is the magnetic field that's going around in the stator. There's a magnetic field from the supply, okay, and it's moving at 60 hertz because that's what we're going to hook to the armature windings in the stator. We're going to hook our supply voltage there, so it's going to create a magnetic field in our three-phase motor that's rotating around within the stator. So even if there wasn't a rotor in there, we would still have that rotating magnetic field. Again, it would be at extremely high current if we didn't have a rotor in there, so we wouldn't do that for very long. But again, we do that example where we put a ball bearing in the stator, and as soon as we bump it with voltage, we see that ball bearing spinning within the stator, showing that there is a magnetic field spinning in there. Okay, that field is running at synchronous speed. So that's a calculated speed based on the number of poles and the frequency. So this motor runs at that speed. So the rotor spins at the same speed as the synchronous speed. And when we talked about squirrel cage induction motors, that was not the case. Our rotor always was slower than the synchronous speed, and then the difference between those was our slip, and then we got a slip percentage based on that. Okay, so everything we've talked about so far for three-phase motors, there was a difference between the rotor speed and the synchronous speed, but in this case, there won't be. Okay, the rotor's going to spin at the exact same speed that the magnetic field is spinning around at. So synchronous motors, again, they require a magnetic field in the rotor to rotate too. Okay, so not only is there a magnetic field spinning around in the stator from the supply, there's also a magnetic field on the rotor. So they'll call this I think a double supply or two supply motor. So we do have two supplies if we're using a field winding on our rotor as opposed to permanent magnets. So again, the field can be supplied by a brushed DC excitation source, brushless excitation source, or a permanent magnet. Okay, so we can have a permanent magnet spinning around in there, or we'll have a set of field windings that can be excited from, again, either brushed or brushless, or potentially even a self-excited scenario. So they have low starting current per horsepower and low starting torque as well. They don't have a good time starting, so we have to aid their starting, so they definitely don't like to be started under load. Okay, so they can operate at a constant speed from no load to full load and maintain maximum efficiency. So constant speed, obviously, again, that's a benefit of it. So here's some applications. Okay, DC generators, fans, blowers, pulp refiners. They are often operated at no load for the purpose of power factor correction, in which they would be called a synchronous condenser. The value of power factor can be changed easily by adjusting the field excitation current. So we'll cover that coming up. If they're used as for power factor correction, they literally would not even have a shaft on the motor. It would just be spinning there, providing leading VARs without a load attached to it. Okay, synchronous motor attached to a VFD becomes a variable speed motor. Variable speed motors are used in applications such as rolling mills, mine hoist pumps, etc. How can a VFD help vary the speed? Well, a VFD is variable frequency drive, and because the synchronous motor runs at synchronous speed, part of that is dictated by frequency. Okay, and we'll get into that formula here coming up, but if I can affect the frequency, I can affect the speed of these motors as well. Okay, so some synchronous motors have permanent magnet poles on the rotor. These machines do not require an excitation system for the rotor. That is 100% true. We would also lose any kind of fine-tuning adjustment for the field if it was a permanent magnet. Okay, so a lot of them don't have permanent magnets because they want the adjustment of the field in order to change the power factor for power factor correction possibly. Synchronous motor compared to a squirrel cage induction motor. The advantages, they can be made to operate at a leading power factor. Okay, obviously a squirrel cage induction motor is always lagging. Give constant speed from no load to full load. Operate at higher efficiency, again, when they're running, especially at unity. Disadvantage, they require DC excitation supplied from a separate source to run, again, if you're not using permanent magnets. They may fall out of synchronism or stop rotating if overloaded. Okay, so we have a maximum load that we have, or it will actually rip it out of synchronism and stop the rotor potentially from spinning. The starting torque is quite small and needs assistance to get to operating speed, and does not work well with applications that require frequent starting or direction change. So again, we can kind of see that the starting is a bit of an issue for these guys. Okay, the starting torque is quite small, again, so we don't want to start it under load, and then starting and stopping or changing directions is not good either. Yeah, that all kind of goes back to the fact that they're not good at starting on their own and they need help to get going. The construction, again, they have a stator and a rotor. This part's going to be very similar to our alternator. We're going to have an armature windings in the stator, and the field is going to be on the rotor spinning around. Okay, so the rotor is different because it supports the field windings. Again, different from a squirrel cage induction motor, potentially because we actually have a separate source going to that rotor as well, that DC source for our field. So it's saying typically an amortisor winding, which is very similar to a squirrel cage rotor bars of an induction motor. Those are also on the rotor, and we'll talk about that. That's for starting. And it's manufactured the same number of poles and field windings as there are poles and armature windings on the stator. Okay. Slip rings and brushes supply the rotor with DC to develop the rotor magnetic field. This allows the rotor to be used as an electromagnet. So once we have that, we have the ability to fine tune that electromagnet and increase or decrease the field intensity based on how much current we have going through those field windings. The squirrel cage amortisor windings is used only to start the motor and has a voltage induced into it just like an induction motor. Like an alternator rotor, it can either be salient or cylindrical pole construction, although most are salient pole. Okay, so again, we got these amortisor windings. We'll talk about how they're embedded into the poles and such, and how they work here coming up for starting. So here's a blowout of the picture. So we have our stator with our armature windings. So we're supplying voltage to the stator, the armature windings in the stator. Here's our brushes, if that's how we're going to bring the DC to the rotor, okay, which has field windings. Okay, here are salient poles, so the protruding ones, not the cylindrical ones. And then we have our amortisor windings. These are like embedded rotor bars almost into the windings for starting. Okay. Synchronous motor operation. This motors are doubly excited, meaning they have two inputs, so the stator and the rotor. Again, the stator is going to get our supply at 60 hertz, and it's going to create a spinning magnetic field within the stator. And then we're going to have the separate DC to the field winding on the rotor that gives us our electromagnet and gives us the adjustment if we can increase or decrease that field intensity. So what this is kind of showing is the north to south direction depending on which peak we are at. Okay, our positive peak, then our negative peak of our C, then positive B, then our negative A. Okay, it's just going to go through in the next picture here and show you that how this magnetic field rotates. Okay, so at each point they've got a picture of the stator and where the magnetic field is going. So it's rotating around this direction, starting here, then point 2, point 3, point 4, point 5, 6, and 7. So you can look at the arrows and see that it's rotating around a full 160-degree cycle till here at 0.7. It's right back to where it started. So it did a full 360-degree turn. What this is basically showing is as these three-phase peaks are happening, positive and negative, it's showing the magnetic field spinning around within the stator. Okay, so if I hook a supply to the stator windings, which are our armature, we definitely get this rotating magnetic field within the stator. Now, that rotating magnetic field, again, is spinning at synchronous speed. That's what we call that. To find our synchronous speed, we use this formula here. So we have our default, our frequency, and our number of poles. That's going to give us our speed here, and that's our synchronous speed. Okay, so the rotational frequency or speed of the stator's magnetic field is directly proportional to frequency of the supply. The greater the frequency, the faster the stator's rotating magnetic field. So here's when they were talking about a VFD. If we could alter the frequency, we can alter how fast it's spinning. Okay, so that's how it can, VFD can help change the speed of this motor. So yeah, use a formula, make sure you can manipulate this formula as well in case they give you the speed and they want to know the poles, etc. Okay, field excitation, the rotating field poles are magnetized by DC flowing through the field windings. You can control the intensity of the magnetic field by varying the field excitation. Varying the current through the field coils controls the excitation. Again, we have talked about this also in DC, this very similar concept. If we can get more current flowing through those field windings, we're going to increase the intensity of that field, and we're going to potentially generate, in alternators, that makes us generate more voltage. We'll see what happens in the synchronous motor as well too. Okay, but the other aspect of the rotor having this magnetic field on it, whether it's stronger or weaker, is to actually try and catch the stator field that's spinning around. Okay, we want to get that rotor to catch and lock up to that magnetic field with its own magnetic field to basically get it to lock into synchronism. Okay, so that's why we need that magnetic field on that rotor. The external DC supply, you can supply a DC voltage onto a spinning rotor with slip rings and brushes the same way as we do on alternators. And again, we can have a field rheostat to adjust the intensity. So again, here they're just showing one pole of the salient pole. Again, the protruding one, not the cylindrical that's made for speed. This one's run at a little slower speed. We have our slip rings and brushes, and we have our DC. This would be an externally excited, obviously, scenario where we have a separate DC source going through brushes and slip rings, and then there's a current flow in this winding creating the magnetic field, okay, for our rotor. Now, the amount of that field intensity is going to be dictated by the current flow. Okay, so we can adjust the rheostat to increase or decrease the current. An increase in current is going to be an increase in the field intensity. You can have brushless as well still. It just uses a rectifier instead of bringing that separate supply. So just again, like we talked about in alternators, the different ways that we can supply that field. Starting a synchronous motor. So this is where the synchronous motor has some trouble. Okay, we want to start it with little or no load so that the rotor can achieve a rotational frequency close to the synchronous speed. If it starts with too much load, the motor provides too much counter torque, and we cannot get enough inertia to get it to start to spin. Okay, so if the motor is at rest and the field and stator windings are energized, it does not begin to turn. The stator magnetic poles pass over the rotor poles too fast for the rotor to lock on and accelerate, so no torque develops. So basically what happens is our field that's spinning at synchronous speed at 60 hertz is going so fast, my rotor that's stationary, that's not moving, even if it has a magnetic field on it, the north and south aren't going to be able to catch the synchronous speed of the stator magnetic field. So it kind of just spins by and passes it by. As one pole's attracted, instantly it's repelled by the next pole that's passing by, and it kind of just sits there and doesn't move at all. So our big goal is to get that rotor to start spinning. Okay, so in my head, I always think, well, even if if you were able to spin it fast enough by hand, you could get it potentially to lock on, excuse me, to that stator field that's spinning around at synchronous speed. but again, obviously not quite practical to stand there and spin it with your hand. So what are some methods we could use? We could have a shaft mounted induction motor, basically to get that rotor spinning, get it up to speed. We could use the load from the synchronous motor as from the synchronous as a starting motor. So for example, it says a DC generator can be converted to a DC motor and used to accelerate the synchronous motor. Or we can use mortiser windings on the rotor. And that's what we're going to talk about the most here. Basically what we're doing is we're going to create these windings embedded in the pole faces that are going to act exactly like the squirrel cage in an induction motor. So it's got complete with end rings. So if I got these bars through and they're completed with end rings, now I have a conductor moving within that, or the conductor is stationary. The synchronous speed of that rotating magnetic field from the supply in the armature windings. So that rotating magnetic field in the stator is going to cut across those closed rotor bars now, or mortiser windings, and it's going to induce a voltage in there. And when it does that, we're going to have current flow in those mortiser windings, and we're going to develop torque to get the motor to start to turn, just like we do with a squirrel cage induction motor. Okay, so we're basically going to try and mimic a squirrel cage induction motor so that it can start just like a squirrel cage induction motor. Okay, so these mortiser windings here are kind of like the squirrel cage, where we're going to have current developing in here after the voltage induced, because we have a magnetic field spinning around here, and we know that when we have a magnetic field spinning around a closed loop conductor, we will get a voltage induced and get current flow. The current flow within these windings is going to create a torque in it and start to spin the rotor around. Okay, so basically we end up starting this just like a squirrel cage induction motor. Now during the process, voltage induced into the rotor windings. Okay, so as we want a voltage to be induced into these mortiser windings, well, there's these windings here too on the field. Okay, they're going to get voltage induced into them, and that's not necessarily something we want. Okay, so they can cause damage in the windings. So to keep the voltage at a safe level, we put a field discharge resistor connected across in parallel, okay, with the field to use using a make before break switch. Once the rotator is rotating at close to synchronous speed, again, it will never get to synchronous speed based on the squirrel cage induction design. The switch will be pressed, then the DC source becomes connected to the field windings, turning them into electromagnets. So again, now we've basically given the induced voltage a path to go around the field windings so they don't get damaged while it's starting. So while it's starting as a squirrel cage induction motor, we want to protect the field windings with this discharge resistor. And then when it's up to speed, up to the speed that it can get, not quite synchronous but close, then we're going to basically take that resistor out of the paralleled location, and we're going to energize the field, creating a magnet. So we had the rotor spinning at almost synchronous speed. Now it's spinning at almost synchronous speed with a magnet on it. Okay, now the electromagnet has been created. So now I have my synchronous field spinning around with a magnetic field, and I have a magnetic field on the rotor spinning at almost the same speed, but not quite. So what's going to eventually happen is now with this new magnetic field spinning here, okay, and spinning in the same direction as the magnetic field from the stator, it's going to eventually try and catch the north and south, will try to line up and lock into each other. So then my rotor will be spinning at the exact same speed as the stator magnetic field. So basically there's a magnetic locking between the rotating field, the magnetic field from the stator, so this on the outside here, and now the magnetic field that's on the rotor. Okay, and when they lock on, then this rotor is going to spin at the exact same speed, which is our synchronous speed. So again, with the induction motor or squirrel cage induction motor, we never got up to that speed because we didn't have this extra magnetic field on the rotor. Okay, but we do for synchronous motor. So that's how we get that magnetic locking. That's how it locks onto the rotating field from the stator. So just like we talked about in DC motors, when we have a magnetic field spinning, and have it basically near another conductor, we're going to induce a voltage in that conductor. So as this field is spinning, okay, now there's a magnetic, as soon as we energize the field windings, now we have a magnetic field that wants to lock onto this, which is great. But we also have a magnetic field now that's cutting across the armature windings. Okay, the armature windings have a voltage going through them from the supply, but they're also going to have now a voltage induced in them from this magnetic field that's spinning around. And we can have a voltage induced into a conductor, even though it has a voltage going through it already. What that's called is counter EMF or counter voltage. Okay, so it's literally counter of the supply, and it's being induced in there from the fact that we have a magnetic field spinning on the rotor now. So it says when the DC windings are energized and the motor is running at synchronous speed, the lines of flux produced by the DC current in the rotor cut across the armature windings of the stator. So now we're inducing a voltage into the armature windings. This voltage is known as CEMF or counter EMF and opposes the supply by 180 degrees. So this is kind of showing it's in general what happens theoretically. I have my phase voltage, okay, this is from my supply. Then I have my generated voltage from the counter EMF being induced back into the armature windings. Okay, so then I get a resultant of that. So I'm going to add my E-gen with my V phase and I'll get a resultant voltage. Now this is showing this at 180 degrees, again, hypothetically. We'll see why it's not quite 180, but theoretically it is counter to the phase voltage, so it is 180 degrees apart. Now when we talk about torque angle, we talk about that magnetic locking. Okay, and that magnetic locking isn't always perfect. It's not exactly at the north and south. There's always going to be a little bit of a drag on that based on the torque of the load. But even if we're not loaded, okay, we're going to see a little bit of a difference there. So they won't exactly line up, again, because we have rotational drag and then potentially mechanical load. So the angle at which it lags is called the torque angle. So that's the angle between the generated voltage and the basically our reference of 180 almost. Okay, so when we look at the phasor diagram for that, there's going to be potentially an angle here, okay, based on, again, that drag or mechanical load that's going to bring this E-gen off the 180. So an angle in electrical degrees is formed when the voltage is represented by phasors. So the torque angle on the phasor diagram illustrates E-gen at 180 out of phase with V phase when it's under load, but lags the 180 degree reference by the torque angle. Okay, so it would be at 180, but then that torque angle is going to kind of take it off that 180 degree reference and move that E-gen right off that 180. Pull in and pull out torque. Pull in is the torque the rotor must develop to pull into synchronism once the field windings have been energized. Again, must be greater than the torque of the load, but we wouldn't want to start these under load if we can avoid it anyways. The pull out torque is the value of load counter torque required to rip the rotor out of synchronism. So if we think about this magnetic locking scenario here, we see that it's pulling the north and south away. That's what gives us our torque angle. Well, if I put too much counter torque or too much load torque on this motor, it's going to basically pull on this north and south so much, increase this angle to a point where it can't take it, and it's going to rip it out of synchronism and break that magnetic lock. And I just kind of think of it like if you've ever had two fridge magnets in your hand, they're stuck together, they're hard to move, but applying enough force will rip those magnets apart. Same kind of deal. If we apply enough counter torque or load torque, it could be enough to rip that motor's magnetic locking apart and get it out of synchronism, okay, which would be a bad thing. So what they say, this situation can happen. It's an overload condition, usually happens when the torque angle exceeds 90 degrees for cylindrical rotors and 60 to 70 for salient pole. So if this E-gen gets around here, 90 degrees, it's going to be at a point where it's going to probably rip it out of synchronism for a cylindrical. For a salient pole, it's going to be at 67 degrees from this reference, from 180. Okay, so if it's 60 degrees, it's going to be sitting at about 120 here, and that would be enough to pull it out potentially as well. So here's an example from page 15 in your module. And I went over it in class earlier, but just to kind of talk about it, saying we got a 600 volt three-phase Y-connected synchronous motor, torque angle of 30 degrees. Okay, so this angle right here is 30 degrees. This is on a phase level, so that 600 volt three-phase Y-connected gives me a phase voltage of 347. Okay, and my E-gen is 400 volts based on the field excitation. Okay, that's what's going to determine this value of E-gen. This is the generated voltage, or CEMF. Okay, and that's based on the strength of that magnetic field on the rotor. So that's going to dictate this value of voltage. Now the load dictates the torque angle. Okay, so we're saying that the field excitation is adjusted, so it's 400. The Z armature of 2 ohms at 90 degrees. The impedance, again, is due to synchronous reactance. That's why it's at 90. We're just saying we're going to ignore the resistance and just use synchronous reactance. That's why that Z is at 90 degrees. Okay, and then we're going to basically get the current of the armature based on the resultant voltage from adding these together. So we're going to take 400 volts. If this is 30, we're going to subtract that from 180. It'd be 400 at 150 plus 347 at 0, and that's going to give us our resultant voltage. Then we take that divided by our impedance, and we'll get the current going through the armature at that time. Again, the resultant is the difference. In this case, we're adding them together, but because the E-gen is almost opposite of the V phase, it's like it's the difference because of where they're sitting on the phasor diagram, but we are definitely adding these at their respective angles and then getting a resultant voltage. That's what's going through the armature winding. Okay, that's what we can dictate. That's what dictates the current. Now the other thing is here is the big thing is that I armature is always going to lag E resultant by 90 degrees. Okay, so this 90-degree relationship right here is always going to apply. Okay, so we can see right now the way this is running, we are running at unity because my current is in phase with my phase voltage. So right now this is showing me current is at unity because there is no lead or lag off the phase voltage. Okay, then in example 2, I just changed the voltage, changed our source again, so now we still get it to a phase. It was at a 240 volt line, 3-phase Y connect. So again, we get the √3 relationship to our phase voltage, and then we have a different value of CEMF, again, based on whatever the field current is. We still add these. Okay, the torque angle in this case was 20 degrees, so we would say 180 at 160, because we're referencing the 20 off the 180. And then we're going to add the 138 at its angle with our V phase and get this E resultant. Okay, so the fact that this torque angle is decreased, it's going to pull the E resultant off a little bit of, in our last example, it was right at 90. Well, now it's kind of leaning more towards here because our torque angle is decreased. We still have to show this 90-degree relationship between the E resultant and the phase current. So what that does is it pulls the phase current off of the 0 reference and gets us into a lead. Okay, so by changing the torque angle, we can change where the current sits too. So by changing the torque angle in this, we've actually got this motor into a leading power factor. Okay, which again we don't usually wouldn't be able to see in a squirrel cage induction motor. So I think I'm gonna stop there, and I'll break it, and then I'll make another video for the loads, and then when we talk about varying loads and then excitation current as well.